Hi everyone, welcome back. We talked about how to write and balance chemical equations last time. So this time we're going to talk about different types of chemical reactions. So we're going to learn to classify different chemical equations as we see them. All right, so there's going to be 5 types of reactions that I'm going to talk about with you: synthesis, decomposition, combustion, single replacement, and double replacement. So one thing that I'd like you to know, just before you know anything about any one of these reaction types, you can probably figure out a little bit about what's going on just by reading the title. Once again, this is a skill that you need to develop, the ability to look at a word and make an educated guess as to what it means. Synthesis, you've seen that word before. You know what synthesis means. It means to make. So in a synthesis reaction, we're probably going to make something. You've heard the word decompose before. Decompose meaning to break down. So we're probably going to break something down in a decomposition reaction. You've heard the word combust before. It probably makes you think of explosion or fire. There's a reason for that. That's because that's what happens in a combustion equation. Single replacement and double replacement may be a little bit harder for you to just guess what's going on, but an educated guess might be we're replacing a single thing in a single replacement versus replacing a double thing or more than one thing in a double replacement. So again, just by looking at the name of these different reactions, you can figure out a little bit about what might be going on in them. So let's start with a synthesis reaction. So that happens when there's a chemical reaction in which 2 or more substances are going to react to produce a single product. So in this case, we have the synthesis of water happening here. We have hydrogen and oxygen reacting together to produce water. So to put this a little bit generally, you could write this kind of A plus B yields AB. And what I mean by that is this could be anything. This is like a variable equation. This didn't have to be hydrogen and oxygen producing water. It could be sodium and chlorine producing sodium chloride. Either way, you have chemical A and chemical B reacting to form some combination of the two. And you can see that there. You see that there's hydrogen and oxygen separately on the reactant side, forming a product that has both hydrogen and oxygen in it. Okay? So there can be a couple of different types of syntheses. There could be 2 elements reacting to form a product, which is similar to what you saw with the hydrogen and oxygen synthesis of water. In this case, we have sodium and chlorine reacting to form sodium chloride. You could also have 2 compounds. In this case, we have calcium oxide and water reacting to form calcium hydroxide. So that one's a little bit less obvious. It's not a clean A-B situation, but there's elements of both things in that product. A plus B equals some combination of A, B. You could also have a compound and an element reacting to produce a different compound. So in this case, we have this SO2 reacting with just plain oxygen, the element 1, to produce that SO3. So again, it doesn't look like a super clean A plus B equals AB situation, but you do have elements of both in that product. So look out for those. Decomposition is next. Again, decomposition, the word means to break down. So shockingly, we're going to break stuff down in a decomposition reaction. So with these ones, you're going to see the exact opposite of a synthesis. Whereas synthesis was A plus B equals AB, we're going to have AB breaking down into A plus B. So the exact opposite thing is happening here. In this case, with this example, we have aluminum oxide breaking down into its base parts, into aluminum and oxygen gas. Okay? So synthesis and decomposition, to reiterate, are opposites of one another. Sometimes it doesn't look as clean as AB yields A plus B. Sometimes you can have something like this go on with a little bit of recombination happening. But another thing to know about decomposition reactions is they don't tend to happen spontaneously. A lot of times they require an energy source, such as heat or light or electricity, to kind of stimulate that reaction to start. Not always. Sometimes it does happen spontaneously, but a lot of times it'll require that energy source to jumpstart that reaction. But what I mean by an unclean decomposition is if you look at this here, this example, I've now split it into that A, B in the reactant side. So we have ammonium here and nitrate there. But if you look on the product side, it didn't split into ammonium and nitrate. It split into something completely different. It actually split into water and this dinitrogen monoxide here. So sometimes that decomposition doesn't happen really, really cleanly. Sometimes it splits a little differently than you might think that it does, but it still follows that pattern of one reactant going towards two products. Okay, so look out for those if you see them. Our third type is going to be combustion. This one is my personal favorite because it's the heat one, the heat, the fire, the explosion one. So the definition of a chemical reaction that occurs when a substance reacts with oxygen, releasing energy in the form of heat and light, is going to be combustion reactions. So this example down here, you probably saw in Living Earth, and if you didn't see it in Living Earth, it means you weren't paying attention, because this is the cellular respiration equation. We have our glucose reacting with oxygen to produce carbon dioxide and water. So when combustion reactions happen, they can release energy in the form of heat or light. Obviously, humans don't glow. We do cellular respiration, but we don't glow, so we're not releasing light there. But it could be a lot more dramatic than that. It could be heat and light. It could be a very violent release of heat and light. It could be a lot of different things. No two combustion reactions are exactly the same. But there are some patterns that you should notice about combustion reactions that are going to help you identify them. They're very easy to identify. And the reason for that is because you are always going to have carbon dioxide and water as the products of your combustion reaction. And oxygen is always going to be present as a reactant, because fire flames cannot exist without the presence of oxygen. You're also going to tend to have a hydrocarbon as your other reactant. So anytime you see carbon dioxide and water as the only products, you're probably dealing with a combustion reaction. Replacement reactions, again, there's two types of them. There's single replacement and double replacement. They involve the replacement of an element or a compound. So there's the two types, single replacement and double replacement. They're going to look a little bit different. So with single replacement, you're going to have the atoms of one element replacing the atoms of another element in a compound. So that sounds kind of confusing. So let's look at this example. Here, with this single replacement reaction, we have one element reacting with one compound to produce an element and a different compound. So if you look at what happens specifically, we have magnesium reacting with copper sulfate. In this case, it's copper 2 sulfate, okay? So the products on the other side is going to be that copper, but now it's magnesium sulfate as your compound. So quite literally, what happened was this magnesium came in and it kicked out the copper to replace it. So that's where that term single replacement is coming from. You have a single element replacing another element in a compound. So that's what's happening there. So this diagram is kind of popular in terms of looking at single replacements. You have this couple dancing over here, and then another guy comes in and says, hey, may I have this dance? And kind of they switch out effectively. And that's exactly what's happening You can see it here as well. In this case, we have lithium as our element. We have water as our compound. On the other side, we have lithium hydroxide as our compound and hydrogen as our element. So quite literally, lithium came in and it kicked out one of those hydrogens over there. And due to the law of conservation of mass, we had to do a little bit of balancing, a little bit of shuffling of things. But largely what happened is lithium is replacing hydrogen in this compound. Okay? So you could have a single replacement happening where it's a metal replacing hydrogen or another metal. So we've seen that already, but in this case here, with this example, we have copper that's coming in to replace the silver. Or you could have the opposite thing going on. You could have a non-metal, in this case fluorine down here, coming in and replacing bromine in this compound. So that reshuffling can happen either metals replacing other metals, or it could have non-metals replacing other non-metals. Okay? So either way, when you have that element plus compound in reactants and you have compound plus element in the products, you're probably looking at a single replacement. Okay? Double replacement is the last one I'm going to talk about, and that is going to involve the exchange of ions between two different compounds. So whereas with single replacement, we were seeing element plus compound yielding element plus compound. In this case, you're seeing compound plus compound yielding compound plus compound. You guys see that? There's a bunch of compounds here. So let's take a deeper dive into what's actually going on. Let's take a look. We have barium chloride and magnesium sulfate reacting with one another. On the product side, we have magnesium chloride and barium sulfate. So quite literally, what's happened here is these two guys have swapped places because barium is bonded to chlorine in the reactants, but barium is bonded to that sulfate in the products. Magnesium is bonded to sulfate in the reactants, but magnesium is bonded to chlorine in the products. So the difference between single and double replacement is really what you're dealing with in terms of single replacement. It's an element replacing another element. And in double replacement, we've got those elements swapping places to form different compounds. Okay? So here's that kind of drawing again, except now we have two couples swapping partners in this little school dance or whatever that's happening up here. And here's another example that you can see. This is actually a subtype of double replacement, also known as neutralization, which is something that we'll talk about in the future when we get to acids and bases. But if you remember anything from acids and bases, you'll know that this is an acid and this is a base. Anything with a hydroxide tends to be a base. Hydrogen bonded to a nonmetal is an acid. And what happens here when things swap out is you end up with a salt and water once those two things neutralize one another. So just a fun fact, neutralizations are actually a subtype of double replacements. One of the more challenging things I'm going to ask you to do this unit is predicting products. So if I gave you two reactants, I might ask you to predict what the products are going to be, given what you know, whoops, went too far, given what you know about the different types of chemical reactions. So that's where recognizing what's going on the reactant side of an equation is really, really, really important, because with a synthesis, you're going to have A plus B on the reactants side. So the example I gave you in the notes was H2 plus O2. So if I said hydrogen and oxygen are going to react to produce what, I would want you to look at that and go, well, they're two elements, so there's really not any breaking down these could really do. So my only option would be to combine them somehow, some way. And so I would want you to be able to tell me, hey, well, I mean, the only compound that I know that has hydrogen and oxygen in it is water, so that might make the most sense. And then if I just said, hey, I have one thing as a reactant, I might want you to be able to tell me, well, if I have this and only this, water is going to do something. The only thing it can really do is break down into its base parts. So I might want you to tell me, hey, water is going to only be able to break down into hydrogen and oxygen gas, which probably sounds like insanity to you right now. It honestly probably does. And I get it, because you're just looking at this type of thing for the first time. But as you see these patterns, they're going to become clear for you. Like, take a look at single replacement. You have a compound and an element. And so if you see compound plus element, that should trigger your brain to be like, hey, a compound plus element, that might be single replacement. So you'll do this type of switcheroo with that type of reaction. And you might be able to accurately predict what your products are going to be. Now, again, we're going to do practice with this. I'm not just going to be like, hey, go, have fun, solve this. I will show you how to do this. But I ask that you bear with me and just kind of take the new information as it comes. And also make sure you have these patterns written down, the AB plus CD yields AC plus BD, because that pattern is going to apply to a lot of things. And then in the last slide, the A plus B yields AB yields A plus B, all that fun stuff, because you can apply that. The confusing one with the pattern is probably combustion, but I promise this is actually the easiest one to predict, because you're always going to have that hydrocarbon and oxygen in your reactant. So every time you see a hydrocarbon and oxygen, you should know automatically that these two things are going to be your products. So combustion looks a little weird pattern-wise, but I promise you it's the easier one to recognize. Okay, so that is all I have to say to you about types of chemical reactions. When I see you after winter break, we're going to do some experimentation. You're going to get to see these types of reactions in action, which is a lot more fun than listening to me talk about it, so you can look forward to that. Other than that, have an amazing winter break, and I will see you when we get back.